Welcome to the Whispering Galaxy, where the cosmos reveals its deepest secrets in the quietest moments. Tonight, we're embarking on a gentle journey through one of the universe's most profound mysteries. A question that has puzzled humanity for over a century and continues to shape our understanding of reality itself. Why does space bend? Before we drift into this cosmic meditation, I'd love to know where you're listening from tonight. Are you nestled in bed somewhere in Tokyo as dawn approaches? Perhaps you're curled up on a couch in Manchester with rain tapping against the window. Drop a comment and let me know. There's something beautiful about imagining our little community of stargazers scattered across the globe, all wondering about the same magnificent mystery. If you're new to the Whispering Galaxy, welcome home. A gentle like and subscribe truly helps this channel reach other curious souls who find peace in pondering the universe's secrets. For those already part of our cosmic family, thank you for being here. Your presence makes these explorations possible. Now, I do hope tonight's topic isn't so fascinating that it keeps you awake, but if it does, at least you'll drift off a little wiser about the elegant dance between matter and space-time. So settle in, let your breathing slow, and prepare to discover why the very fabric of reality curves and flows like a cosmic river. For most of human history, space seemed like the simplest thing imaginable. Empty, still. A vast container holding stars and planets like ornaments in a cosmic display case. We thought of it as a stage where the drama of the universe unfolded, but never as an actor in the play itself. Space was just there, passive and unchanging, providing a backdrop for motion without participating in it. This view felt natural because it matched our daily experience. When you walk across a room, the floor beneath your feet seems solid and reliable. The air around you appears transparent and weightless. Everything suggests that space is nothing more than the absence of stuff, a void waiting to be filled. Even the greatest minds accepted this picture for centuries. Isaac Newton gave us laws that described motion beautifully within this framework. Objects moved through space according to predictable rules. Forces acted across distances in mysterious but measurable ways. His equations could predict the path of a comet or the swing of a pendulum with stunning accuracy. The universe seemed to run like clockwork, with space serving as the fixed frame upon which all motion was measured. But there was always something troubling lurking beneath this elegant picture. How could forces act instantly across vast distances? When the Earth pulls on the moon, how does the moon know to respond? Newton himself admitted he had no answer. He called it action at a distance and confessed it seemed almost magical. Yet the mathematics worked so perfectly that most people simply accepted the mystery as part of nature's design. Then came observations that didn't quite fit. The planet Mercury, closest to our Sun, traced an orbit that shifted slightly over time in ways Newton's laws couldn't fully explain. Starlight seemed to behave strangely near massive objects during solar eclipses. These were tiny discrepancies, barely noticeable, but they hinted that something fundamental was missing from our understanding of space and gravity. The revolution began quietly in the mind of a young patent clerk in Switzerland. Albert Einstein possessed a rare gift for seeing the universe from unexpected angles. While others accepted the mysteries of gravity as unsolvable, he dared to ask a different question entirely. What if gravity isn't a force at all? Einstein's great insight came from imagining himself in an elevator. Picture yourself sealed inside a windowless box, floating in the emptiness of deep space. You release a coin, and it drifts beside you, weightless. There's no sensation of up or down, no pull in any direction. This, Einstein realized, is what the absence of gravity actually feels like. Now imagine the same elevator, but this time the cable has snapped and you're falling freely toward Earth. Inside the plummeting box, something remarkable happens. You still feel weightless. The coin still floats beside you. From your perspective within the elevator, gravity has vanished completely. You and everything around you fall together at exactly the same rate, creating the illusion of zero gravity. This thought experiment revealed something profound. The feeling of weightlessness during free fall and the sensation of floating in deep space are identical. Einstein called this the equivalence principle, and it became the key that unlocked a new understanding of the universe. If falling freely feels the same as floating in empty space, then perhaps gravity isn't pulling you downward at all. Perhaps something else entirely is happening. Einstein's revolutionary idea was breathtakingly simple, yet profound beyond measure. What if space and time themselves aren't separate, fixed entities, but form a single, flexible fabric? What if massive objects don't pull on other things across empty space, but instead curve this fabric, creating valleys and slopes that guide motion naturally? Imagine stretching a rubber sheet taut and placing a heavy bowling ball in the center. The sheet dimples and curves around the ball's weight. Now roll a marble across the sheet. Instead of traveling in a straight line, it follows the curve, spiraling around the depression created by the bowling ball. The marble isn't being pulled by any mysterious force. It's simply following the easiest path available across the curved surface. This analogy, while imperfect, captures the essence of Einstein's vision. Replace the rubber sheet with space-time itself, the bowling ball with a star or planet, and the marble with light or matter moving through space. Suddenly, what we call gravity becomes geometry. Objects don't fall because they're pulled downward. They follow the natural contours of curved space-time, like water flowing along the bed of a river. The implications were staggering. Space and time, once thought to be absolute and unchanging, became dynamic participants in cosmic events. They could stretch, compress, and ripple in response to matter and energy. Time itself could slow down near massive objects, flowing like thick honey compared to the swift current of time in empty space. This wasn't merely a new theory about forces. It was a complete reimagining of reality itself. The universe transformed from a mechanical clock into something far more organic and alive. Space-time became a medium that could dance with matter, responding to its presence while simultaneously guiding its motion. Einstein's equations, published in 1915, describe this cosmic choreography with mathematical precision. They showed how the distribution of matter and energy determines the curvature of space-time, and how that curvature, in turn, influences the motion of everything within it. Matter tells space-time how to curve, and space-time tells matter how to move. Written in the language of geometry, it's a conversation beauty of this picture lies in its unity. A falling apple and an orbiting planet obey the same fundamental principle. They both follow geodesics, the straightest possible paths through curved space-time. What looks like curved motion to us appears perfectly straight from the perspective of four-dimensional space-time geometry. Light, too, participates in this cosmic dance. Though photons have no mass, they still follow the curves of space-time, bending around massive objects like streams of water flowing around stones in a riverbed. This predicted bending of light became one of the first dramatic confirmations of Einstein's theory. As we drift deeper into this exploration, we'll discover how this elegant vision explains everything from the ticking of atomic clocks to the spiral arms of galaxies. We'll see how space-time can ring like a bell when massive objects collide, sending ripples across the cosmos that we can now detect with extraordinary precision. The universe revealed by Einstein's insight is mechanical cosmos, far stranger and more beautiful than the of Newton. It's a place where geometry comes alive, where space and time dance together, and where even emptiness itself has structure and meaning. In this curved cosmos, nothing moves alone. Every motion is a response to the shape of space-time, and every massive object contributes its voice to the grand geometric symphony. Tonight, we'll follow this thread through some of the most profound discoveries in physics exploring how the bending of space explains phenomena that once seemed miraculous. From GPS satellites adjusting their clocks for relativistic effects, to black holes twisting space-time into impossible knots, we'll see how curvature shapes every aspect of our cosmic experience. The story begins with time itself, that most fundamental river flowing through our existence. We take it for granted, assuming it moves at the same steady pace everywhere in the universe. But Einstein's curved cosmos revealed something extraordinary. Time doesn't march forward uniformly. It bends, stretches, and slows, depending on where you are and how much mass surrounds you. Picture two identical clocks, crafted with perfect precision. Place one at sea level and carry the other to a mountaintop. Leave them there for a year, ticking away in perfect synchronization. When you return, something magical will have occurred. The mountain clock will have gained a few nanoseconds, running slightly ahead of its companion below. The difference is minuscule, invisible to human perception, yet undeniably real. This happens because time flows faster where gravity is weaker. At higher altitudes, farther from Earth's mass, space-time is less curved, allowing time to run more freely. Down at sea level, where the gravitational field is stronger, time moves through thicker cosmic honey, slowing by the tiniest fraction. Your smartphone knows this secret. Every GPS satellite orbiting high above must account for this time dilation, adjusting their clocks continuously to maintain accuracy. Without these relativistic corrections, your navigation would drift by several kilometers each day. The maps on your phone would show you driving through buildings or walking on water. Modern civilization quietly depends on Einstein's insights, running on curved space-time without most of us ever realizing it. This warping of time becomes more dramatic near truly massive objects. Imagine a clock placed near a neutron star, where matter is compressed to impossible densities. Time would slow to such a degree that seconds for the clock would stretch into minutes for distant observers. Near the event horizon of a black hole, time dilation becomes so extreme that it appears to stop altogether from an outside perspective. The universe's most massive objects don't just bend space, they knead time itself into new shapes. Light, that eternal wanderer of the cosmos, also responds to space-time's curves. Though photons carry no mass, they must still follow the geometry laid out by matter and energy. When starlight passes near our sun during a solar eclipse, it bends by precisely the amount Einstein's equations predict. The star appears slightly displaced from its true position, shifted by gravity's invisible hand. This bending of light transforms the universe into a natural telescope. Massive galaxies act as cosmic lenses, magnifying and distorting the light from more distant objects behind them. Sometimes the geometry aligns so perfectly that we see multiple images of the same distant galaxy, or even complete rings of light called Einstein rings. The universe photographs itself through gravity's lens, revealing cosmic structures that would otherwise remain hidden in darkness. These gravitational lenses have become invaluable tools for astronomers. By studying how light bends around galaxy clusters, scientists can map the distribution of dark matter, that invisible substance that outweighs ordinary matter by 5 to 1. The dark matter doesn't emit or absorb light, but its gravitational influence curves space-time just enough to leave fingerprints in the shapes of distant galaxies. When we zoom out to examine orbits, the poetry of curved space-time becomes even more apparent. The Earth doesn't circle the Sun because of some invisible tether pulling it inward. Instead, our planet follows the straightest possible path through the curved space-time created by the Sun's mass. What appears to us as circular motion is actually straight-line travel through four-dimensional geometry. Think of it this way. If space-time around the Sun were perfectly flat, Earth would drift away in a straight line, never to return. But the Sun's mass creates a depression in the cosmic fabric, and Earth continuously falls into that depression while moving forward. The result is an elegant loop. an orbit that represents the perfect balance between motion and curvature. This same principle governs every celestial dance, from Mercury's swift race around the Sun to the leisurely waltz of distant Pluto. Each world traces its own geodesic through space-time, following paths determined not by mysterious forces, but by pure geometry. The asteroid belt, the rings of Saturn, even the graceful spiral arms of galaxies all emerge from this fundamental relationship between matter and the shape of space. Mercury, being closest to the Sun, provided one of the first crucial tests of Einstein's theory. For centuries, astronomers had noticed that Mercury's orbit wasn't quite closing on itself. Each time the planet completed its journey around the Sun, its point of closest approach shifted slightly forward. Most of this precession could be explained by the gravitational influences of other planets, but a small remainder of about 43 arc-seconds per century remained mysterious. Newton's laws couldn't account for this tiny drift, but Einstein's curved spacetime explained it perfectly. Mercury wasn't misbehaving, it was faithfully following its geodesic through the more intensely curved spacetime near the Sun. The planet's orbit was precessing because spacetime itself was twisted in ways Newton had never imagined. The confirmation of this prediction helped establish general relativity as more than just an elegant mathematical exercise. Here was a theory that could explain real observations with precision, revealing the hidden geometry underlying celestial mechanics. What had seemed like a small anomaly in Mercury's motion became a window into the fundamental structure of reality. As we venture further into this cosmic meditation, we encounter phenomena that stretch our imagination even more dramatically. When massive objects accelerate or collide, they create ripples in space-time itself. These gravitate outward at the speed of light, ational waves spree carrying information about the cataclysmic events that birthed them. For nearly a century after Einstein predicted their existence, gravitational waves remained purely theoretical. They seemed impossibly faint, stretching space by amounts smaller than 1,000th the width of a proton. But human ingenuity eventually caught up with cosmic subtlety. In 2015, the LIGO detectors achieved the extraordinary feat of measuring these cosmic whispers directly. The first detected signal lasted only a fraction of a second, but it told an incredible story. Two black holes, each dozens of times more massive than our Sun, had spiraled together in a death dance lasting millions of years. In their final moments, they merged with such violence that they shook the very foundations of space-time, sending ripples racing across billions of light years to tickle our laser interferometers on Earth. Since that historic detection, we've learned to listen to the universe's gravitational symphony. Each collision produces its own signature, its own cosmic song. Neutron star mergers create different melodies than black hole collisions. The frequency, duration, and amplitude of these waves tell us about the masses involved, their spins, and the nature of matter under the most extreme conditions imaginable. These discoveries have opened an entirely new window on the cosmos. We no longer just observe the universe through light and other electromagnetic radiation. We can now feel its heartbeat directly through the medium of space-time itself. Gravitational wave astronomy lets us witness events that produce no light, exploring the dark side of cosmic evolution. The detectors themselves are marvels of precision engineering. Each LIGO facility consists of two 4-kilometer-long arms arranged in an L shape. Laser light bounces back and forth between mirrors at the ends of each arm thousands of times. When a gravitational wave passes through, one arm stretches while the other compresses by an amount so small it defies comprehension. Yet this microscopic change in the interference pattern of the laser light reveals the passage of ripples in spacetime itself. Future gravitational wave observatories will push these measurements even further. Space-based detectors like the proposed LISA mission will create triangular arrays millions of kilometers across, sensitive to lower frequency waves from even more massive black hole mergers. These instruments will let us probe the early universe in ways never before possible, perhaps even detecting the gravitational echoes of cosmic inflation itself. The beauty of gravitational waves lies not just in their exotic nature, but in what they represent. They're direct evidence that space medium, when a time is indeed a dynamic, responsive, massive objects dance together in the cosmic ballet, space-time itself becomes their stage and their music, vibrating with the rhythm of their motion. The universe doesn't just contain waves, it becomes the wave. As our exploration deepens, we'll discover how this curved cosmos shapes everything from the smallest atomic clocks to the largest galaxy clusters. We'll see how space-time can twist and swirl around spinning objects, dragging nearby matter along like leaves caught in a cosmic whirlpool. The story of curved space-time is still being written, with each new discovery adding verses to this grand poem of geometry and motion. The implications of curved space-time extend far beyond the grand theatre of colliding black holes and distant galaxies. They whisper through the most intimate details of our daily existence, shaping the very atoms that compose our bodies and the light that fills our rooms. Every breath you take, every heartbeat, every thought that drifts through your consciousness unfolds within this curved cosmic medium. Consider the humble atom, that tiny universe of particles bound together by forces we can barely comprehend. Within each atomic nucleus, protons and neutrons huddle together against the explosive force of electromagnetic repulsion. What keeps them united isn't some cosmic glue, but the curvature of space-time at the smallest scales imaginable. The strong nuclear force, one of nature's fundamental interactions, emerges from the geometry of space-time twisted into dimensions we cannot directly perceive. Even more remarkably, the very stability of matter depends on this geometric dance. Electrons don't crash into atomic nuclei because they exist in quantum probability clouds, but those clouds themselves are shaped by the subtle curvature of space-time around each atom. The Pauli exclusion principle, which prevents electrons from occupying identical quantum states, is intimately connected to the topological properties of curved space-time. In a very real sense, your existence depends on geometry. The photons streaming from your reading lamp right now carry the memory of every gravitational field they've encountered on their journey. If that light originated from atoms in a power plant, it has been subtly redshifted by Earth's gravity as it climbed away from the planet's surface. The effect is vanishingly small, but it's there nonetheless. Each quantum of light bears the invisible signature of space-time's curvature. This phenomenon, known as gravitational redshift, occurs because light must expend energy to escape from gravitational wells. As photons climb out of curved space-time, they stretch to longer wavelengths, their colors shifting slightly toward the red end of the spectrum. The effect becomes dramatic near extremely dense objects like white dwarf stars or neutron stars, where light can lose significant energy in its escape to open space. Astronomers use this stretching of light as a cosmic scale, measuring the depths of gravitational wells across the universe. The more redshifted the light from a star's surface, the more compact and massive that star must be. It's a technique that has revealed some of the most exotic objects in the cosmos, places where matter is compressed to densities that dwarf anything achievable on Earth. The reciprocal effect also occurs when light falls into gravitational wells. Photons gain energy as they descend through curved space-time, becoming blue-shifted toward higher frequencies. This subtle dance of light and gravity plays out constantly throughout the universe, with every beam of radiation serving as a messenger carrying news of the space-time geometry it has traversed. Perhaps nowhere is the interplay between curved space-time and everyday technology more apparent than in the global positioning system. Those quiet satellites orbiting high above our heads are engaged in a continuous conversation with Einstein's equations, their atomic clocks ticking to the rhythm of relativistic corrections. The satellites experience two competing effects that would have seemed like pure fantasy to earlier generations. Their high orbital velocity causes their clocks to run slightly slower due to special relativity, while their distance from Earth's gravitational field makes them tick faster due to general relativity. The net result is a daily drift of about 38 microseconds, tiny by human standards, but enormous in the precision world of satellite navigation. Without accounting for these relativistic effects, GPS accuracy would degrade by several kilometers each day. Your phone's confident declaration that you're standing at a specific street corner depends entirely on engineers who understand how space-time curves around our planet. Every turn-by-turn direction, every location pin dropped on a map, represents a quiet victory of Einstein's geometric vision over the classical assumptions of absolute space and time. The same principles govern the synchronization of financial networks, where transactions worth billions of dollars must be time-stamped with microsecond precision. The Internet's backbone relies on atomic clocks that account for gravitational time dilation, ensuring that data packets arrive in the correct sequence, regardless of the altitude of the servers that route them. Modern civilization runs on curved space-time, though most of us never pause to appreciate this remarkable fact. As we venture deeper into the cosmos, space-time reveals even more extraordinary behaviors. Around spinning objects, something truly magical occurs. The rotation doesn't just create curvature in space-time, it drags the very fabric of reality around with it. This phenomenon, known as frame dragging or the lens-thirring effect, transforms space-time from a passive medium into an active participant in cosmic rotation. E-time as a thick, imagined space, viscous fluid surrounding a spinning top. As the top rotates, it stirs the fluid around it, creating swirling currents that extend far beyond the object itself. Near a rotating black hole, this effect becomes so pronounced that nothing can remain stationary. Even light is forced to orbit in the direction of the black hole's spin. This dragging of space-time has been measured right here on Earth using some of the most precise instruments ever created. The Gravity Probe B mission placed 4 perfect spherical gyroscopes in orbit around our planet, monitoring their orientation with extraordinary precision. Over the course of a year, the gyroscope's axis of rotation shifted by exactly the amount predicted by Einstein's equations, confirming that our planet's rotation does indeed drag space-time around with it. The implications ripple outward through astrophysics. The powerful jets of material that shoot from the poles of rotating black holes may be powered by this frame-dragging effect. As space-time swirls around the black hole, it can extract rotational energy and channel it into these cosmic searchlights that stretch across millions of light-years. The geometry of space-time itself becomes an engine, converting the spin of collapsed stars into some of the most energetic phenomena in the universe. Near the most extreme objects in the cosmos, black holes, space-time curvature reaches its ultimate expression. These aren't holes in space at all, but regions where matter has collapsed so completely that space-time curves back on itself. The event horizon marks the boundary where all possible paths lead inward, where even light cannot escape the geometric inevitability of the black hole's pull. What happens at the center of a black hole remains one of physics' greatest mysteries. Einstein's equations predict a singularity, a point of infinite density where the known laws of physics break down. But most scientists suspect this mathematical infinity signals the limits of our current understanding rather than a true physical reality. Somewhere in those extreme conditions, quantum mechanics and general relativity must merge into a theory we have yet to discover. The approach to a black hole reveals space-time curvature in its most dramatic form. Time dilation becomes so extreme that a clock falling toward the event horizon would appear to slow to a crawl from an outside observer's perspective. The falling clock would seem to freeze just above the horizon, its light growing ever redder until it fades from view. Yet, from the clock's own reference frame, time passes normally as it crosses the boundary and continues its inexorable journey inward. This strange duality of perspectives hints at the deeper mysteries that curved space-time still holds. Reality itself seems to depend on where you stand. and how you move through the cosmic landscape. There's no universal now, no absolute simultaneity that all observers can agree upon. Instead, each traveller through space-time carries their own version of the present, their own slice through the four-dimensional block of existence. The study of black holes has also revealed unexpected connections between gravity, thermodynamics, and information theory. These cosmic laboratories, where space-time reaches its breaking point, seem to encode information on their surfaces in ways that challenge our understanding of how reality stores and processes data. The holographic principle suggests that everything happening inside a black hole might be fully described by information encoded on its two-dimensional boundary, like a cosmic hologram projecting three-dimensional reality. These discoveries point toward an even deeper truth about the nature of space-time itself. Perhaps the curved geometry that Einstein revealed is not the fundamental layer of reality, but an emergent property of something more basic. Some theorists propose that space-time itself might arise from the quantum entanglement of more fundamental entities, with geometry emerging from information rather than the other way around. The search for quantum gravity, a theory that would unite Einstein's curved space-time with the probabilistic world of quantum mechanics, remains one of physics' greatest challenges. String theory proposes that the fundamental constituents of reality are vibrating filaments existing in dimensions beyond our direct perception. Loop quantum gravity suggests that space-time itself is quantized, built from discrete units of area and volume at the smallest scales. Each approach offers tantalizing glimpses of a deeper reality where the smooth curves of Einstein's geometry give way to something more granular and strange. Yet the classical picture of curved space-time continues to govern everything from GPS satellites to gravitational wave detectors, proving its worth across an extraordinary range of scales and phenomena. As our instruments become more sensitive, we continue to probe the limits of Einstein's geometric vision. Precision tests of general relativity push toward ever smaller deviations from predicted behavior, searching for cracks in the theory that might reveal new physics lurking beneath. The recent detection of gravitational waves has opened entirely new avenues for these investigations, allowing us to study space-time curvature in its most dynamic and extreme manifestations. The future promises even more extraordinary revelations as we learn to listen more carefully to space-time's whispers. Advanced gravitational wave detectors will peer deeper into cosmic history, perhaps detecting the primordial ripples left over from the universe's inflationary birth. Space-based observatories will map the large-scale geometry of the cosmos with unprecedented precision, searching for subtle signs of curvature on the grandest scales imaginable. Networks of atomic clocks scattered across Earth and beyond will transform our planet into a giant gravitational wave detector, sensitive to distortions in space-time that current instruments cannot perceive. These quantum chronometers will also probe the fundamental nature of time itself, testing whether temporal flow remains uniform even under the most careful scrutiny. The story of curved space-time is still being written, each new chapter revealing fresh layers of beauty and mystery in the cosmic architecture. What began as Einstein's attempt to understand gravity has blossomed into a comprehensive worldview that touches every aspect of physical reality, from the quantum foam that may bubble at the smallest scales to the grand curvature that shapes galactic superclusters. Geometry reigns supreme as the language in which the universe writes its deepest truths. In this curved cosmos, nothing moves in isolation. Every particle, every wave, every thought that passes through your mind participates in the grand geometric symphony that is space-time. The boundaries between observer and observed, between matter and the medium through which it moves, dissolve into a seamless whole where everything influences everything else through the subtle medium of curvature. As you drift towards sleep tonight, consider that your dreaming mind will trace its own geodesics through the landscape of consciousness, following paths as natural and inevitable as those taken by planets orbiting stars. The same geometric principles that govern the cosmos may shape the very thoughts that carry you into slumber, weaving meaning from the curved space-time of imagination itself. The relationship between space-time and consciousness opens doorways to questions that hover at the very edge of scientific understanding. If geometry shapes the paths of particles and planets, might it also influence the neural pathways that give rise to awareness itself? The brain, after all, is a collection of atoms obeying the same curved space-time that governs distant galaxies. Every electrical impulse that carries a memory or sparks a dream unfolds within this cosmic medium. Consider the delicate dance of neurons firing in synchronized patterns, creating the experience you call your thoughts. These electrochemical signals propagate through curved space-time, just like any other physical process. The calcium ions flowing across synaptic gaps, the quantum tunneling events that may influence neural computation, even the electromagnetic fields generated by brain activity all participate in the same geometric framework that Einstein revealed over a century ago. This perspective suggests something profound about the nature of mind itself. If consciousness emerges from the complex interactions of matter and energy, then it too must be shaped by the curvature of space-time. Your memories aren't stored in some abstract realm separate from physics. They exist as patterns of connection within neural networks, patterns that exist within and are influenced by the curved geometry of the cosmos. The speed of thought itself may reflect these deeper geometric constraints. Information cannot travel faster than light, even within the biological circuits of the brain. The time it takes for signals to propagate between different regions of neural tissue creates the temporal structure of consciousness. The flowing stream of awareness that feels so immediate, yet actually unfolds across measurable intervals of curved space-time. Some researchers have proposed that quantum effects in microtubules within neurons might be responsible for certain aspects of consciousness. If true, these processes would be exquisitely sensitive to the local geometry of space-time. The quantum coherence that allows particles to exist in multiple states simultaneously could be influenced by gravitational fields so weak that we can barely detect them with our most sophisticated instruments. This quantum perspective on consciousness suggests that your awareness might be fundamentally non-local, spread across space-time in ways that mirror the quantum entanglement of particles. The boundary between your mind and the cosmos becomes less distinct when viewed through this geometric lens. You don't simply exist within space-time. You are a localized expression of its curvature, a temporary eddy in the flow of cosmic geometry. The implications ripple outward through philosophy and physics alike. If space-time curvature influences consciousness, then massive objects might subtly affect the quality of awareness experienced nearby. The gentle time dilation near Earth's surface could create imperceptible differences in the flow of thought compared to the experience of consciousness in the emptiness between galaxies. These ideas remain largely speculative, dancing at the intersection of neuroscience and cosmology where few experimental tools can reach. Yet they offer a tantalizing glimpse of how deeply the geometry of space-time might penetrate into the most intimate aspects of existence. Your capacity to wonder about these very questions may itself be shaped by the curved medium through which your thoughts propagate. As we transition from the realm of consciousness back to the observable cosmos, we encounter phenomena that stretch our understanding of what curvature can accomplish. In the vast spaces between galaxies, space-time reveals its most subtle and far-reaching behaviors. Here, in regions so empty that a handful of hydrogen atoms might be separated by volumes larger than Earth, the geometry of the universe displays its grandest architecture. Dark energy, that mysterious pressure driving the accelerating expansion of space itself, operates through mechanisms we are only beginning to glimpse. Unlike the localized curvature created by stars and planets, dark energy appears to be a property of space-time itself, an inherent elasticity that causes empty space to stretch at an ever-increasing rate. This cosmic stretching doesn't pull galaxies apart through space. It creates new space between them. The effect transforms our understanding of cosmic evolution. Distant galaxies aren't flying away from us through a pre-existing void. Instead, the spacetime that separates us from them grows larger with each passing moment. Light traveling from these remote regions must traverse an expanding geometry, its wavelength stretched along with the space it moves through. This cosmological redshift carries the signature of universal expansion, encoding the rate at which spacetime itself evolves. Current observations suggest that dark energy makes up roughly 70% of the universe's total energy budget, yet its nature remains profoundly mysterious. It might represent the quantum vacuum energy of empty space, a subtle effervescence of virtual particles that creates a gentle outward pressure. Alternatively, it could signal the presence of new fields that permeate the cosmos, dynamic entities that drive expansion through mechanisms we have yet to discover. The measurement of dark energy's effects requires observing objects at cosmic distances where the accumulated expansion becomes noticeable. Type 1a supernovae serve as cosmic candles, exploding with predictable brightness that allows astronomers to calculate their distances. By comparing these distances with the redshift of the host galaxies, scientists can map the expansion history of the universe with remarkable precision. The results paint a picture of cosmic evolution that would have astonished earlier generations. For the first several billion years after the Big Bang, the expansion of space was gradually slowing as matter and gravity worked to pull the cosmos back together. But roughly 5 billion years ago, something changed. The expansion began to accelerate, as if some cosmic force had awakened and started pushing space apart with increasing vigor. This acceleration continues today, and if current trends persist, it will shape the ultimate fate of everything we can see. Distant galaxies will recede beyond the cosmic horizon, their light stretched to wavelengths so long that they fade from view. The universe will become an increasingly lonely place, with only the local cluster of galaxies remaining visible to any observers who might exist in that far future. Yet even this grand cosmic story unfolds within the framework of curved spacetime that Einstein revealed. The expansion of space, the acceleration driven by dark energy, the formation of cosmic structures across billions of light years, all represent different expressions of the same geometric principles that govern falling apples and orbiting satellites. Scale changes the details, but geometry remains the underlying language. On the largest scales we can observe, space-time appears remarkably flat despite all the local curvature created by individual objects. This cosmic flatness represents one of the most precise measurements in all of science, confirming that the overall geometry of the universe deviates from Euclidean flatness by less than 1%. Draw a triangle with sides spanning billions of light years, and its angles would add up to almost exactly 180 degrees. This near-perfect flatness poses deep questions about cosmic origins. In most theoretical models, the universe should have been born with significant curvature that would either cause it to collapse quickly or expand so rapidly that structure never forms. The observed flatness requires the total energy density of the cosmos to balance on a knife edge between these extremes, a coincidence so precise that it cries out for explanation. The theory of cosmic inflation provides one possible answer. This proposes that the very early universe underwent a period of exponential expansion, stretching any initial curvature to scales far larger than the portion we can observe. Like inflating a balloon to enormous size, this process would make any small region appear perfectly flat, even if the overall structure remains curved. Inflation also offers explanations for other cosmic mysteries, such as why the universe appears so uniform in all directions despite regions that have never been in causal contact. If all the matter we can see today was once compressed into a volume smaller than an atom, then it had time to reach thermal equilibrium before inflation stretched it across cosmic scales. The quantum fluctuations that existed during inflation may have been stretched along with space itself, creating the tiny density variations that eventually grew into galaxies and galaxy clusters. In this view, The cosmic web of structure we observe today represents the fossilized imprint of quantum uncertainty from the universe's first fraction of a second. Testing these ideas requires pushing observational techniques to their absolute limits. The cosmic microwave background radiation carries the faint signatures of inflationary physics, encoded in subtle temperature variations across the sky. Future space missions will map these fluctuations with unprecedented precision, searching for the distinctive patterns that different inflationary models predict. Gravitational waves may also carry information about cosmic inflation, though detecting them would require sensitivity far beyond stretching of spacetime during inflation would have current capabilities. The violent generated a background of gravitational radiation that might still be detectable today. Finding this primordial signal would provide direct evidence for the geometric processes that shape earliest moments. As we approach THED, our universe's limits of observational cosmology, the questions become increasingly profound. What lies beyond the cosmic horizon, in regions so distant that their light has not yet had time to reach us? If the universe is indeed infinite in extent, then every possible configuration of matter might exist somewhere in the vast expanse beyond our view. There could be regions where the laws of physics themselves are different, domains where space-time curves in ways our current theories cannot describe. These speculations bring us full circle to the fundamental mystery that sparked our journey. Why does space bend? The answer, we've discovered, is that space and time are not the fixed backdrop for physical events that our intuitions suggest. They are dynamic, responsive, and intimately connected to everything that exists within them. Matter and energy tell space-time how to curve, and space-time tells matter how to move. This conversation between geometry and substance creates the rich tapestry of phenomena we observe throughout the cosmos. From the quantum foam that may exist at the smallest scales to the gentle curvature that guides galactic evolution, geometry emerges as the fundamental language of nature. Every equation in physics, every natural law we have discovered, ultimately describes relationships within this curved space-time framework. Even the constants of nature, those unchanging numbers that define the strength of forces and the masses of particles, may themselves be geometric properties of higher dimensional spaces. The story continues to unfold as our instruments become more sensitive and our theories more sophisticated. Each new discovery adds another verse to the cosmic poem written in the grammar of curvature. We are part of this poem, temporary arrangements of matter and energy moving through the curved medium that gives structure to existence itself. The atoms in your body were forged in the cores of ancient stars, where extreme space-time curvature enabled the nuclear processes that created heavy elements. The calcium in your bones, the iron in your blood, the oxygen you breathe, all emerged from cosmic furnaces where geometry and physics dance together to synthesize the building blocks of life. Your DNA carries information that has been shaped by billions of years of evolution on a planet orbiting through curved space-time. The genetic code itself may reflect geometric principles we are only beginning to understand, patterns that emerge naturally from the interplay between information and the physical laws that govern its storage and transmission. Even this moment of quiet contemplation participates in the grand geometric symphony. The electromagnetic radiation carrying these words to your eyes, the neural signals processing their meaning, the thoughts and emotions they evoke, all unfold within the curved space-time that Einstein revealed over a century ago. As sleep approaches and consciousness begins to fade, remember that your dreaming mind will continue to trace its own geodesics through the landscape of imagination. The same principles that guide starlight around massive galaxies may shape the paths of memory and dream, weaving meaning from the curved space-time of inner experience. The boundary between waking and sleeping, between consciousness and dreams, represents another kind of horizon in the space-time of awareness. Beyond it lies a realm where the usual rules of logic and causality bend like light around a black hole, creating new possibilities for connection and understanding. In dreams, space-time itself becomes malleable, allowing impossible journeys and impossible meetings. Past and future collapse into an eternal present where all moments exist simultaneously. The geometric constraints that govern waking experience relax, permitting the mind to explore configurations of reality that the physical universe forbids. Yet even in dreams, some deeper geometry persists. The emotional resonances that give dreams their meaning, the symbolic connections that link disparate images, the narrative threads that weave experience into story, all reflect patterns that may be as fundamental as the curvature of space-time itself. The universe dreams too, in its own vast way. Quantum fluctuations in the vacuum create temporary virtual particles that flicker into and out of existence, like thoughts arising and dissolving in cosmic consciousness. The expansion of space itself might be understood as the universe exploring all possible geometries, testing different configurations of curvature across the infinite expanse of potential realities. In this cosmic reverie, where physics and philosophy merge into one flowing meditation, we find ourselves approaching the most profound mystery of all. The question that whispers beneath every equation, every observation, every moment of wonder as we gaze into the star-filled night. What is the true nature of existence in a universe where space itself can bend and flow like water? The answer, perhaps, lies not in any single discovery, but in the accumulation of countless small revelations. Each gravitational wave detected by our instruments adds another note to the cosmic symphony. Precision. Every measurement of atomic clocks ticking at different altitudes contributes another brushstroke to the portrait of curved space-time. The universe reveals itself gradually, gently, like dawn breaking over a vast landscape we are only beginning to explore. Consider the extraordinary fact that you're experiencing this moment at all. The probability that the exact arrangement of atoms comprising your consciousness would come together in this particular configuration, at this precise instant in cosmic history, borders on the miraculous. Yet here you are, a temporary eddy in the flow of space-time, capable of contemplating the very medium that gives structure to your existence. Your thoughts right now are propagating through neural networks that obey the same geometric principles governing distant quasars. The electrical impulses carrying these ideas from one synapse to another follow geodesics through curved space-time, just as surely as light bends around massive stars. There is no separation between the cosmic and the intimate, between the vast and the personal. All existence participates in the same fundamental dance of geometry and substance. This perspective transforms our understanding of what it means to be alive in a curved universe. We are not separate observers looking out at space-time from some external vantage point. We are expressions of space-time itself, localized concentrations of matter and energy that have organized themselves into patterns capable of self-reflection. The universe has developed the ability to contemplate itself through conscious beings like us, creating a feedback loop between observer and observed that may be as fundamental as any physical law. The implications ripple outward through every aspect of human experience. Art, music, literature, love itself, all emerge from the complex interactions of particles moving through curved space-time. The beauty you perceive in a sunset reflects electromagnetic radiation that has traveled along geodesics shaped by the sun's mass. The emotions stirred by a piece of music arise from sound waves propagating through air molecules, each following the contours of local space-time geometry. Even our deepest philosophical questions about meaning and purpose take on new dimensions when viewed through this geometric lens. If consciousness is indeed an emergent property of sufficiently complex arrangements of matter, then the search for meaning becomes the exploration of how space-time organizes itself into increasingly sophisticated patterns. We are the universe's attempt to understand itself, temporary arrangements of atoms that have developed the capacity for wonder. The future of our species may depend on how well we learn to navigate this curved cosmos, As we venture beyond Earth, whether to other planets or eventually to other star systems, we will need to master the subtle art of moving through space-time with precision and grace. Our spacecraft will trace geodesics between worlds, their trajectories calculated not by Newton's simple laws, but by Einstein's elegant geometry. The technologies we develop for these journeys will push our understanding of curved space-time to new limits. Fusion rockets that harness the same nuclear processes powering stars will need to account for relativistic effects as they accelerate to significant fractions of light speed. Navigation systems will require atomic clocks accurate enough to detect the gravitational influence of asteroids and comets. Communication networks will need to compensate for the time dilation experienced by travelers moving at high velocities. Perhaps most remarkably, we may learn to use space-time curvature itself as a tool for exploration. Gravitational slingshot maneuvers already allow our probes to gain energy by following carefully calculated paths around planets and moons. Future technologies might harness the frame-dragging effects of rotating massive objects, or even find ways to manipulate space-time geometry directly. The concept of warp drive, though still purely theoretical, represents as bold humanity dares attempt to work with curved space-time rather than against it. Instead of accelerating through space at tremendous energy cost, such a propulsion system would contract space-time ahead of a spacecraft while expanding it behind, allowing faster-than-light travel without violating relativity. The vessel itself would remain in a bubble of flat space-time, never actually exceeding the cosmic speed limit. While such technologies remain far beyond our current capabilities, they illustrate how profoundly our relationship with space-time may evolve. We are learning to see geometry not as a constraint, but as an opportunity, a medium rich with possibilities for those who understand its subtle rules. The same curvature that keeps planets in orbit might one day carry us to distant stars. As our instruments become ever more sensitive, we continue to discover new layers of complexity in space-time structure. The recent detection of gravitational waves has revealed that space itself can ring like a bell, vibrating with harmonics that carry information across cosmic distances. These ripples in geometry may hold keys to understanding the deepest mysteries of existence, from the nature of black hole interiors to the quantum structure of space-time itself. Advanced gravitational wave detectors planned for the coming decades will peer deeper into the cosmic past than any optical telescope. They may detect the echoes of cosmic inflation itself, those primordial gravitational waves that would carry direct information about the universe's first fraction of a second. Such observations could reveal whether our cosmos is part of a vast multiverse, whether time itself has a beginning, and whether the laws of physics remain constant across cosmic epochs. As we reach the gentle end of tonight's journey through curved space-time, let the profound truth settle softly around you like starlight. Space bends because it must, responding to every grain of matter with elegant precision. You are not separate from this cosmic dance, but woven into its very fabric, following geodesics through dreams and waking moments alike. Thank you for sharing this exploration with the Whispering Galaxy family. Sweet dreams, fellow travelers, and may your rest be as peaceful as the universe's quiet geometry.